Hey guys, welcome to section 6.2 for science. Today we're getting into the section of expansion and heat transfer. It's been a while since we started chapter 6, I understand, but remember we're talking about heat. So we've already talked about thermal energy and heat capacity, and specific heat, but now we're going to be talking about methods of heat transfer, and we're going to be talking about expansion. Guys, it's actually really interesting. Okay, so you're going to be taking some time to process today, honestly. Okay, there is no math involved with today. There's just concepts about how heat expansion and transfer works. Okay, there's three different types of heat transfer. Don't worry, this is not what I'm asking you to take notes on right now. I'm just letting you know as an introduction. There are three types of heat transfer. There's conduction, convection, and radiation. Today you're going to be learning about conduction. On the next one you're going to be learning about radiation and convection. But before you get into that, you're also going to be learning about expansion. It's like mind-boggling, you guys, about expansion. Some of you guys are really interested in engineering, interested in architecture, and it's important, it's super important to understand a little bit, for right now in the introduction stages of it, to understand that it's important to understand how heat expands and how cooling contracts certain substances, certain materials, okay? Because you need to understand that if you're building a bridge, if you're building a building, you're working with different material. You're working with cement, you're working with steel, you're working with aluminum, you're working with copper. You're working with different materials that expand and contract at different times because of heat and how sensitive they are to the cooling process, that you have to understand what works together and what doesn't work together. And so I hope you find this chapter pretty interesting. In the middle of your notes today, it's going to get a little like, I'm sorry, what did you say? But then you're going to get back into, oh, okay, this is making sense, right? Okay, so it just takes a little bit of processing. Let me tell you what I want you to take notes on first today, and then we'll kind of go into a little bit more so I give you something to grab onto to understand a little bit about this, okay? What you're going to do first is you're going to tell me 4 interesting facts you learned from the introduction to this chapter. What is the introduction to this section, where it says expansion and contraction. Okay, expansion and contraction here to this spot right there. Okay, is your introduction. 4 interesting facts that you learn. What do you learn about the bridge? Okay, what do you learn about building a bridge? What do you learn about expansion and contraction? Like, for example, maybe you guys have never done this. I honestly have never done it. I just heard that it works. Like, let's say that you have a metal jar, a glass jar with a metal lid. Okay, glass jar, metal lid. In order to get that lid off, I always just beat it on something, like to hit the metal a little bit up and then twist it off. But I've also heard people say that you can also put the jar into hot water or warm water, or run warm water over it. Why? You guys know why? Because what happens is, look, it says it on the second paragraph right here. Metals and plastics expand more than glass. So the metal lid will expand because you put water on it. It's going to get bigger than the glass. Glass does not expand as much. Glass is not as sensitive and flexible. By putting hot water on it, it's not going to expand, but metal does. So you got a jar now that's glass, but you've got the lid that's metal. The lid is going to expand and come off the jar easier because heat was applied. I think that's pretty cool. Okay, so you're going to do 4 interesting facts there. Then I want you to write 6-sentence paragraph. Listen, because I want you to process this, you guys. A 6-sentence paragraph on the why is the expansion of water unique? Why is the expansion of water unique? Okay, there are 3 paragraphs there telling you about the expansion of water. Listen, I'm going to just introduce it to you. Then I want you guys to process the rest of it. It says, unlike most substances, water stops contracting at 4 degrees Celsius. It expands as it cools below this temperature. When the temperature reaches 0, there is a sudden expansion as the water freezes. Because of this expansion, the density of ice is much less than the density of liquid water. If cooling continues after ice forms, the ice contracts slightly as it gets colder, just as other materials do. So what happens, you guys, is that usually when substances are cooling, they contract, okay? So they get smaller, they squeeze in, okay? And depending on the substance, it does that exageradamente or it does it very, very little. Okay, just like the expansion of metal is bigger than the expansion of water. And honestly, you know that this is all on the microscopic level, so it's not like you're gonna, really observe it like looking at it 5 feet away, right? Same thing with contracting. But as water is cooling, like let's say you put water in the freezer and it's getting colder and colder and colder, about to get to ice, it gets smaller and smaller and smaller until it hits 4 degrees. And after it goes below 4 degrees, it says it expands as it cools below this temperature. And then when it hits 0 again, it suddenly expands as water freezes. So it's getting ready to become ice. From 4 degrees to 0, it starts to expand because it's starting to make ice crystals. And then as soon as it is ice, it expands more. Not other substances do that at a certain cold temperature, it's going to start expanding again. Okay, so the last paragraph of this section about why is the expansion of water unique is very interesting because it talks about how God created it to where ice is going to float instead of sink, which is why some parts of nature work the way that they do, because of this fact that the expansion of water is unique to other substances. Okay, super interesting. So take time to process through that. Okay, then you're going to give me 3 sentences on how a thermostat works. I'm going to come back to that in a second. How a thermostat works, which is on page 133. And then I'm going to give you 4 sentences on how does conduction work. Remember, we're talking about the 3 types of heat transfer. You need to research today on how does conduction work. Okay, and then I want you to give me a paragraph about how does the miner's safety lamp work that Sir Humphrey Davey made. Okay, how does the safety lamp work that Sir Humphrey Davey made? And 2 sentences about who Sir Humphrey Davey is, okay? I'm going to give you a video at the end of this. If I don't, someone please tell me. Thank you. To send out the link. It's a 5-minute video on how the miner's safety lamp works. So you can read through it here, but they're going to give you really good information as well in the video. Okay, so let's just go over really quick. I already started jumping into it because I got a little excited, okay? So I'm telling you, expansion and contraction does a lot, okay? The metal lid, the glass jar. Also, if you're looking at a clock, there are certain clocks that have metal handles, and when it's hot outside, those metal handles are going to expand and actually set the time off. It's going to get, the time's going to go a little weird because it's starting to read it a little bit too fast because it's expanding its arm, its hand, the metal hand, during the heat of the summer, okay? I already talked about the expansion of water, so let's go into the thermostats. Okay, what is a thermostat? I'm telling you that you have to write it down how it works. I'm going to tell you a little bit in everyday language. A thermostat is anything inside an electrical device that needs to control temperature. So, for example, your air conditioning your house. Not the air conditioning we have here, but there's internal air conditioning and internal heating systems, which means that, look, if I have my air conditioner over there, if I want it to turn on, I hit the button and it turns on. And I choose what temperature level it's on, right? But if you have an internal air conditioning system, it's going to kick on and off all day according to what temperature you have set to maintain in your house. The thermostat is going to decide if it needs to get colder or warmer inside the house to meet that level that you want, okay? So if you go into a house, you're going to see like an air conditioning system. Let's say that I want it to be 75 degrees inside the house. It's going to say, okay, you want this temperature of 75 degrees. The actual temperature inside the house is 76 degrees, which means that the thermostat right now is working to cool it down. okay? But it's also working against the heat outside that's pumping into your windows. So it might not always be the same temperature until the thermostat can bring it down, okay? So that can happen in electric irons. It can happen in electric blankets. It can happen in toasters. It can happen in ovens. It can happen in refrigerators, especially. You put the temperature that you want. Now it needs to regulate it using the thermostat to get it to that temperature, using all of the things, all the considerations that it has around it, all the circumstances, right? The heat outside, and the products and materials inside, right? So how does it work? Well, look at paragraph number 2, because this is kind of confusing, so I want to help you with it. Some thermostats have a bimetallic strip that responds to temperature changes. So you can see what it looks like inside a machine, like right here. Okay, this is a bimetal strip. That means it has copper and steel, I believe is what they're going to tell us. Yeah, copper and steel inside this little like spiral thing, okay? Copper and steel expand and contract in different ways. So it's bimetallic because it has 2 metals, okay? Look what it says, that respond to temperature changes. A bimetallic strip, which by the way, you can see a little bit right here, but this is not what it looks like. It looks like this inside the thing. They're just showing it to you a little zoomed in. Consists of 2 metal strips, such as one is of steel and one of copper, that are bonded together. When heated, the copper expands about 1.4 times the length that steel does, okay? But that's going to trigger something, okay? So here you go. You have steel and you have copper, okay? If it gets hotter, the copper is going to expand more than the steel does. So the temperature change causes the strip to bend from one side to the other, okay? One side to the other. And so here's the steel and here's the copper, and it's going to either expand this way or contract this way, okay? According to the heating and cooling. The bending can operate an electrical switch. So if it's going to hit this way, it's going to hit an electrical switch to either cool down or get hotter, depending on what the purpose of the thermostat is. And then if it hits this way, it's going to hit an electrical switch to do the same thing. To do something different according to the heating and cooling. Okay, when the temperature in the room falls, the copper contracts more than the steel does. As the strip bends toward the copper, it activates an electrical strip switch to turn on the heater. When the temperature increases, the expanding copper causes the strip to bend toward the steel so that the arm moves in the other direction to deactivate the heater. Okay, thermostats can also use the expansion and contraction of other materials, etc., etc., etc. Okay, so it's all about hitting the switch on and off according to the copper expanding and contracting on top of that steel. That's a thermostat, and it can be used in a lot of different ways. Okay, and then the first paragraph of the types of heat transfer is talking about thermal energies, reviewing what we learned the last time, which is good for a review because we haven't talked about it in a while, okay? But look what it says. Although heat, I'm on page 134, first full paragraph. Although heat flows in only one direction, remember that's from high temperature to low temperature, heat flows from hot cocoa to your tongue in a different way that heat travels from the sun to the earth. Okay, so heat travels in 3 different ways. That's what we just said. Or how it spreads through the ocean. It's either by conduction, convection, or radiation. Okay? Conduction is super easy to understand, and you can see a really good picture here. Conduction is where one thing that's hot is touching another thing that's hot, and it transfers that heat. Okay? So, for example, if you put a metal piece of something inside a fire, what's going to happen? Let's say that this is a metal rod, and you put it inside the fire. What's going to happen over here? It's going to burn your hand because it conducts heat very, very well. Metal does. And then it's going to heat up your hand as well. That's conduction. Okay, it's a direct relation. You put something inside the fire, that thing is going to transfer the heat. That's conduction. Okay, it says right here, the process by which heat flows through materials and between objects in direct contact is conduction. Especially when there's a good conductor of heat, that can cause problems and can act fast. Okay, it's fully and well explained here about what conduction is. And then the minor safety lamp. Sir Humphrey Davey taught in the Royal Institution in London, and the video I'm going to show you comes from the Royal Institution. Okay, a man that also works there is going to explain this invention, okay, and it's going to explain how it revolutionized people working in the minas, in the mines, okay, because it was always a very dangerous place, you guys. A lot of people died working in there, but it was the only way to make money, to survive, to provide for your family in certain areas around the world. In England, for instance, different parts of Europe, also in the United States, it was huge as well. So this invention that he did that was so simple, honestly, so simple, but it was because of his understanding about heat conduction that made it possible for it to be a revolutionary invention for the people that worked in the mines. You have to pay attention, you guys, and you have to write about it. You cannot avoid writing about it. How the gauze, which is the tela, the screen around the lamp, makes it a safe lamp. You have to write about that part. Okay, how the tela, the gauze around the lamp, makes it so safe. How does that work? It's mentioned in the video. It's alluded to here, but it's mentioned very well in the video at the end. You have to listen to it, okay? And then don't forget to write 2 sentences on Sir Humphrey Davey, because I want you to see him. He's a Christian guy and really did a lot for science, because he believed that science was very applicable to life, because he believed what God said about it, about his creation and about the laws of nature. Okay, guys, so enjoy learning today. There's just 4 pages, but it's a lot to process, so I want to give you time to do that. Bye.
Now, you might be wondering why I've set this romantic candlelit scene up for myself, and it's because I want to talk to you today about fire damp. Now, fire damp is something that in the early days of coal mining caused lots of horrific accidents and killed hundreds of miners, and here's why. Now, that was methane, which is extremely flammable and one of the main components of fire damp, which is a gas that used to leak from the coal-bearing rocks in the mines. Now, the miners in those days only had naked flames like these candles to light their way, so the result was inevitable. Now, the reason I'm interested in all of this is because the solution to this problem was devised by a scientist working right here at the Royal Institution. That man was Humphrey Davey, a chemist whose simple invention revolutionised the mining industry and helped to fuel Britain's Industrial Revolution. So I've come down to the RI's archives to look at some of Davey's early attempts to tackle this problem. Over here we've got some of the prototypes that didn't work quite so well, but then here this is what Davey ultimately come up with. So this is the miner's safety lamp, or the Davey lamp. And you can see that it's a really simple solution to the problem. It's just an oil lamp, the wick enclosed in this piece of gauze here, this cylinder of gauze. And it's the gauze that's doing the work. The gauze is what prevents the flame from igniting the gases in the mines and creating an explosion. And all of these actually, Davey made all of these within about 2 months in 1815. He was really working hard at this problem because he knew that other people were trying to solve it at the same time and he wanted to get in there first. And this was so successful, this design, that this commercial version on the right here was actually made around 50 years after Davey's prototype here. Which shows that it was used almost unchanged for decades down in the mines and keeping people safe. So, how does a Davey lamp work? Well, to give you an idea, I've filled this tube with natural gas, which is mainly methane and similar in composition to fire damp. Now, if I ignite it at one end, you can see that the flame front propagates along the tube in quite a spectacular way. But if this time we insert a bit of gauze in the centre of the tube and repeat the same thing, we can see that the flame stops at the gauze. The gas itself is able to pass through the gauze no problem, but the flame isn't. You can see that if I light the tube again from the other end, the second part of the tube still has gas in it and so is still able to burn. Well, Davie discovered that flames don't propagate through small holes, and you can see that even more clearly if I hold this gauze over this candle flame. He spent ages experimenting with tiny metal tubes and different gauzes trying to find exactly the right size hole for this job. Now, all fires and all flames need to sustain a high temperature in order to burn. And normally that's quite easy because the chemical reaction itself releases lots of heat, so that the high temperature becomes self-sustaining. But if you can cool the reacting gases down fast enough, then you can stop the flame in its tracks, and that's what the gauze does. The metal wires that form the gauze absorb all the heat from the flame, cooling it to the point where it can't sustain itself. So I have a replica of one of Davie's early lamps here, and down in the mines these lamps allowed naked flames to be used relatively safely. If there was any fire damp in the air, it would pass through the gauze into the lamp and burn relatively innocuously there, rather than igniting the gas on the outside. And that's quite a difference from what we saw earlier. Once Davie had perfected his design, it not only allowed miners to mine more safely, but also to mine deeper and more productively, so coal output soared. But the reason I like this story is that it's a great example of applied science. Just by careful experimentation and observation, Davie was able to find a simple solution to a big problem.